Hello and welcome to our quick introductory video to chemical synthesis. So today there's a couple of items on the agenda. The first thing I'm going to do is give you a quick background on chemical synthesis pathways, as well as this topic of chemical synthesis in general in your Year 12 syllabus. And secondly, the big thing on the agenda today is giving you a framework for approaching these chemical synthesis style questions. So guys, these tend to be 5, 6, sometimes 7 markers towards the end of your exam, and usually require a longer, more detailed response. To answer them effectively, it's important you walk into the exam, that is, with a really well-structured framework. There are two main things that you need to understand and describe when answering most of these questions. Not all, most of these questions. So you need to understand how a chemical synthesis is designed and how it's made more efficient. And there's some factors that affect this, and we'll go over those factors today. And there are also some socio-economic factors that are associated outside of that design that affect the chemical synthesis. So we'll also be going over those today. The framework that we established today, we established together that is, we will be building on with some separate videos using this exact same framework and covering the main chemical synthesis that you need to know in your Year 12 syllabus. One of the big ones is the Haber process, and there's a couple others for each where we will have some separate videos. So the theme for chemical synthesis is essentially making a product that is in need and is commercially viable, and making it as cheaply and efficiently as possible by using the principles that we've learned in chemistry. Tying all of that together, an example is ammonia and the Haber process. So the Haber process is the chemical synthesis pathway for ammonia, which is a commercially viable product. We use ammonia in a lot of uses. One of those is fertilizer. As demand for ammonia increases, we can't afford to have a process that isn't cheap or isn't efficient. We need to maximize the amount of ammonia that we're getting. We need to maximize our bang for buck. There are three main things we need to consider. So what will the chemical be used for? Or rather, how much demand is there for the actual chemical? And that is, you can answer that part with the uses for it. So if it's used very commonly, such as ammonia and fertilizer, you need fertilizer everywhere. It'll be used often and there's a big demand. So you need to establish that there's a demand for the thing you're trying to make. Next, we need to actually design a chemical synthesis pathway that ensures we can make the most of what we're trying to make, the commercially driven product, in as efficient and cheap a manner as possible. So there's a couple of factors that affect this. Number one, yield. The concept of yield, I'll just underline that. There's two concepts that you need to understand: yield and reaction rate. Yield is for every gram of reactant, how much product are you getting by percentage? So a higher yield is desirable. So you want to maximize the yield. So if I have 100 grams of my starting reactant, you want to look at a yield of, say, in the 90%. So for 100 grams, you're getting, say, 95 grams of product. So that would be a yield of 95%. There's a couple of factors that affect yield, and we'll go over them in a couple of slides' time. And also reaction rate. So it's all well and good having a high yield. So if I put 100 grams of reactant, I'm getting, say, 98 grams of product. So that's a really good yield, 98%. However, if this is a slow reaction that's happening over days or hours, it's not commercially viable. So we need to try and maximize both. We need to try and make as much as we can, so maximize the yield, and as efficiently and as in a quick time manner as we can, so maximize the reaction rate as well. So these two concepts are integral. We maximize the yield and the reaction rate by applying the concepts that we've learned in Year 12 and a bit of Year 11 chemistry, especially with Le Chatelier's principle, activation energy, and catalysts. So we'll tie all of that in. Lastly, to answer these questions, this last point here is really important. So, number one, the product that you're making, is it environmentally friendly or is it detrimental to the environment? The process that you're using to maximize yield and reaction rate, is it environmentally conscious? Socially, are you doing it in a socially acceptable or an ethically acceptable manner? Or are you cost cutting and using unacceptable or unethical practices? So those are all considerations that you need to take into account when answering these questions. So we'll split up our discussion into two sections. So for the first section, we'll cover some of the factors that affect making a good chemical synthesis pathway. So again, those come down to maximizing your yield and reaction rate. So that's the first part of our discussion. And in the second part of our discussion, we'll go over some of the socio-economic considerations that you need, especially not only when answering questions, but also getting you to think about wider implications of these chemical synthesis pathways on society, really. So these have a real world application as well. So the first of these factors that affect chemical synthesis is the availability of reactants. So guys, a theme that you'll be seeing developing over the course of this video and also chemical synthesis as a whole is we'll be kind of touching on a lot of the concepts that we've learned in Year 12 chemistry. The first of which we need to have a good discussion about is Le Chatelier's principle. With the availability of the reactants, the reason why that's a big consideration is because it's a primary or really easy way to maximize your yield. So Le Chatelier's principle states that if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium shifts to counteract that change that you've imposed, right? So if I have a chemical synthesis, so say A and B are reacting to form C. A really easy way to make more of C is to add A and B in excess, so a lot of A and B. Now, if I've added a lot of A and B, I've obviously disrupted this dynamic equilibrium that I have. The system is going to shift in a way to minimize the effect of that change that I've imposed on the system. So thus, if I add an excess of reactants, the system will shift from left to right and make more of the product, which is what I want. I want more of C. So that's a really easy way to maximize your yield. Now, one of the things you need to think about when answering these questions is it's all well and good saying we need to have increase in the concentration of the reactants, right? It's really easy to say that. However, that's not entirely easy as it sounds, because some reactants might not be that easy to trace. So you might only be able to find trace concentrations of some reactants. You can't afford, or it's not financially viable to dump them in excess. So you need to find other ways to maximize your yield. But for reactants that are relatively common, this is a really easy, surefire way of maximizing your yield by adding them in excess. Another thing that can affect the design of a chemical synthesis is temperature. So we can actually use temperature in a twofold way. So whilst the availability of the reactants will mostly affect the yield, temperature has the effect of potentially affecting the reaction rate as well as the yield. So an increase in temperature will increase the reaction rate. This is because temperature is a reflection of the average kinetic energy of each of the particles. Now, if I increase the temperature, I increase the average kinetic energy of each of the particles in your reaction vessel. So thus, when they collide, that increased temperature, or rather that increased kinetic energy or average kinetic energy, means that more particles will have the sufficient activation energy for a successful collision. So thus, your rate of reaction will increase. This is a really easy way of increasing your rate of reaction. However, we can also tie in Le Chatelier's principle in regards to temperature. If the chemical synthesis is an exothermic process, so it looks something like this. So I'll use my A and B example again. A and B reacts to form C and releases some heat. Ignore my weird H. So this is an exothermic process. A way in which we can increase the yield is by decreasing the temperature. Again, let's tie in Le Chatelier's principle. There's a complete video on Le Chatelier's principle, but we can revisit some of that today as well. So, if I decrease the temperature, the system is going to shift in a way to minimize the change that I've imposed. So I've decreased the temperature. We're going to try and make more heat to try and counteract that change, right? So it'll be shifting from left to right to make more of C. The converse is also true. So if I rub that out, if it's an endothermic process, so I'm using up heat to make C, so that's an endothermic process. If I increase the overall temperature of the system, right, I've imposed a change. The system will shift in a way to minimize the impact of the change that I've imposed. So if I increase the temperature for a reaction that's endothermic, it's going to shift again from left to right and increase my yield. So in this way, temperature can affect both the reaction rate. So an increase in temperature can affect the reaction rate. However, temperature can also independently affect the yield, and so that's an important consideration for you to make. Like temperature, pressure also can affect both the reaction rate as well as the yield. So we'll start with the yield first, and I'll use my example of A and C again. Now, instead of A plus B reacting to form C in a dynamic equilibrium, this time 3 molecules of A plus 2 molecules of B react to form only 2 molecules of C. Now what you're about to see is an application of Le Chatelier's principle in regards to pressure. So if I increase the pressure of this system, I increase the pressure of this reaction, I've imposed a change. The system is going to shift in a way to minimize the impact of that change. So if I have an increase in pressure, the system will shift from left to right to minimize the overall amount of molecules in the reaction vessel, right? So I've increased the temperature. It's already really crowded. On the left, the system can shift to the left side and it has 5 molecules, or it can shift to the right side where it has 2 molecules. Obviously, think of a bus. If it's really crowded in the bus, are you going to want 5 more people on the bus, or would you rather 2 more people, right? Obviously, you're going to go for 2 more people because you don't want it to be crowded. So thus, higher pressures favor reactions that produce the least number of gaseous molecules. Conversely, the opposite is also true. Lower pressures favors the reaction that produces the most number of gaseous molecules. So yield is directly affected by pressure. However, the rate of reaction is also affected by yield. So increasing the pressure of the system increases the overall concentration of the reactants, so they're overall closer together, and thus more likely to collide in a successful manner because they're just closer together. Another thing should be stated. So there's a reason I put gaseous molecules in red. Pressure, or an increase in pressure, will only affect the yield of gaseous chemical synthesis pathways. If A and B, so I'll say 3A plus 2B reacts to form 2C. If these are all solids, and I put them in I increase the pressure of this system, it will not affect the yield in any discernible manner, or at least in a manner that's significant for year 12 chemistry. So if you are applying an increase in pressure, make sure your reaction has gaseous molecules in it. That's the key takeaway. So the last thing that can affect the chemical synthesis pathway is the use of a catalyst. So firstly, what is a catalyst? A catalyst is something that speeds up or makes a reaction more efficient by increasing the reaction rate, but does not directly participate in the reaction itself. So it's neither consumed nor used. Catalysts do not affect the yield of the reaction, so they do not directly help you make more of your product. What they can do is affect the reaction rate. This is because catalysts make the process more efficient. So they provide an alternative pathway for the reaction to occur with lower activation energy, and that is the money statement: lower activation energy. if you lower the activation energy, overall, more particles will have sufficient energy to kind of jump over that threshold, right? So if more particles are jumping over that threshold, more particles are reacting successfully, and thus the rate of reaction will increase as a result of the catalyst. So it's important to also say that catalysts are not consumed. So if something is consumed, it's not a catalyst. As a result of using the catalyst, it's a really, really efficient and cheap way of increasing your reaction rate. So that means as a consequence of, you can actually run the reaction at much lower temperatures. So I know I said that the rate of reaction rather increases with increased temperature. However, increases in temperature, you need to factor cost in. Increases in temperature are incredibly expensive to keep running for a prolonged period of time. If you can use a catalyst and get that increase in temperature anyway, right? What is the point of keeping a sustained increase in temperature where you're just burning fossil fuels? And not only is that using money, it's also bad for the environment, right? So catalysts have a twofold kind of advantage. So not only do they help increase your rate of reaction, they also allow you to run the overall chemical synthesis pathway at a lower temperature. So just to recap, there are a couple of things that affect the chemical synthesis pathway. So temperature, pressure, using a catalyst, and the availability of the reactant. So that is what you have in your control, and you can play around with these factors in the chemical synthesis that we're going to go over in the following video, such as the Haber process. We're going to be playing with each of these factors and trying to maximize the amount of product that we're making. Aside from that, there are some socio-economic issues that we need to cover. So number one, economics. So money runs the world. Temperature especially, or increases in pressure, are incredibly expensive to maintain and further sustain for a prolonged period of time. So you need to factor that somehow, and if you can get away with using a catalyst, go for it. Number two, plant equipment. So the chemical synthesis needs to be cheap and efficient. So there's no point, if you have a yield of 99%, but it costs you a lot to maintain and use, because you need state-of-the-art equipment to maximize your yield. Versus if you get a yield of 95% but you're using basic materials and a basic plant. You're obviously going to take the 95% because overall it's not worth that small increase in yield for that huge plant, right? So as you can see, it's kind of a trade-off. So we do want an increase in yield and reaction rate, but there is a cost to it, a literal cost to it. Number three in economics, reactants. So we need to source reactants that are scarce. So we need to source reactants that are not scarce, actually, that are present and ready to be used whenever. One thing you need to consider is the chemical synthesis I'm designing. Although it might be efficient, if my initial reactants are both scarce and expensive, can I design an alternative pathway that does the same thing, albeit with a lower yield and a lower reaction rate? However, the reactants are a lot more available and overall the process will be a lot cheaper. If that's the case, you obviously go for the cheaper option, depending on what the sacrifice in yield is. That's something you've got to judge. Environmentally, there are a couple of things we need to consider. So the big things are the production of CO2 and fossil fuels in two things. So sourcing your reactants. So obviously you have to get your reactants somewhere. A lot of it involves mining for a lot of these reactive processes or chemical synthesis processes. So how much CO2 and fossil fuels are you using when you're actually getting the reactants? Number two, how much CO2 and fossil fuels are you using when you're actually making the product? So how efficient is your chemical synthesis pathway? And that kind of ties in with temperature, because obviously your temperature has to come from somewhere, and that unfortunately largely relies on the burning and use of fossil fuels, and conversely the production of CO2, which has its own umbrella problems. We'll be going over those in a couple of videos time. So with each of the processes, such as the Haber process, they have the production of CO2 and the environmental impacts have kind of their own nuances that we'll discuss. However, just keep in mind, if you ever get stuck and you don't know what to put for the environmental section of a question, just put down production of CO2 when actually sourcing the reactant, and then production of CO2 when actually making the chemical synthesis. Lastly, we need to discuss the social impacts. So the product that you're making, is it socially viable? Is it good for the environment? Are you making it in a socially acceptable or ethically responsible manner? Are you housing your ingredients ethically? So those are all the things that we need to consider, and very important things when you're discussing the question. So discussing the answer for a question, that is. So these questions tend to be really beefy, 5, 6, sometimes even 7 or 8 markers in the exam. So they're going to be expecting a lot of information. So make sure you really drain every single bit of detail that you can, especially when with the factors that affect your chemical synthesis. So temperature, pressure, the catalyst, and the availability of the reactants, and also the socio-economic issues. Make sure you absolutely milk it.